Hello, hello. Welcome, Lucia. Hello there. Are you ready for some learning? Did you do the contest? The weekly? We're going to be doing that in the stream. We're going to be doing that live. You didn't? Okay. So maybe you can help me provide a fresh look into the problems. So let me share the link so that you can. I'm gonna pin this. And let's get started with question 1. I'm gonna share the link. It's called minimize operations to equalize array. So you are given an integer array nums of length n, and in one operation choose any subarray from L to R inclusive, and you can replace each element in that subarray with the bitwise AND of all elements. Return the minimum number of operations required to make all elements of nums equal. A subarray is a contiguous, non-empty sequence of elements within an array. Okay, so when you read this, you might be a little bit surprised if you notice that this is kind of a trick question, right? Because it's pretty easy to notice that if you apply the operation to the whole array, right? If you choose, they tell you that you can choose any subarray, right? So that includes the whole array, right? And that would automatically make all the elements the same, right? Even regardless of what the operation was, right? It doesn't, even if it was something else. If you're gonna do something with that subarray, some operation, and then you're going to assign that result to each element in the subarray, then they will necessarily end up being the same. So that proves that you can always make them all equal with one operation. Question is, maybe they are already all equal, and then you don't need any operation, right? You need 0. And so that's the only thing that you need to choose. You need to see, right? So we have to check if they are all the same. So one way to do that would be to create a set with the numbers to see if they are all if there's only one unique element, right? That's a way to do it. And that's it. So it takes 3 milliseconds. So I think it's interesting this idea that the operation didn't matter, right? That's one point that I'm making. So this is really a trick question. Anyway, so another way, so yeah, so this run in 3 milliseconds. what if I do, instead of doing this way, what if I, instead of using a set, I just check that all of them are equal to the first one? Is that going to make any difference? Hey, thanks for the follow, Alex. Thank you. So, well, it ran in 0 milliseconds, but the difference is so small that I'm not sure if it's just measurement error or if it fumbled my interview. Hey, Rallo Gomez. Welcome. You fumbled your interview, so well, you're here. Don't worry, you'll have another chance. Let's learn together. So my point of so sometimes in competitive programming in Python, since the set is a hash table internally, is not the most efficient. Well, in this case, the numbers are even the size is even small, so it really doesn't matter. But yeah, so know that there are different ways of doing it, right? And sometimes you want to avoid using set because this is simpler. So let's move on to question 2. I'm going to share the link. Minimum operations to transform string. So you are given a string S consisting of only of lowercase English letters. You can perform the following operation any number of times, including 0. Choose any character Z in the string and replace every occurrence of C with the next lowercase letter in the English alphabet. Return the minimum number of operations required to transform S into a string consisting only of A characters. Consider the alphabet as circular, thus A comes after Z, right? Okay, and you have like 5 times 10 to the 5th characters you can have. Okay, so any ideas? Any ideas when you read this? What do you think? What are you thinking? So I think the first thought that I have is that still parsing the problem statement. Okay, sorry. I think the first thought that I would have here is that notice that the operation is applied to all the occurrences of the letter, right? So and they all had to be transformed into A, right? So it doesn't matter. So the multiplicity, the number of occurrences doesn't matter, right? You could have if you have 1 or 2 or whatever, it's going to be the same. Also, the order, the position in the string, that's not going to matter, right? This is just so you can think about the input as a set, right? You can even convert it, right? You can even do something like this, and it should be the same answer, right? Even without knowing how to solve this yet, right? then notice, so another thing that we can notice is that if we have, so let's say we have a C in the string, and let's say we have also an E and an F, right? So notice that when we apply the operation to the one that is farthest from A, which is going to be the smallest that is not A, right? Because the A's, of course, you don't have to transform them. You can ignore them. But here, the smallest one that is not A is C, right? So that's the one that is going to have the longest distance to A. And notice that if you change this, you apply the operation once and you change this to D, and then you apply the operation again and you change it to D. Now, when you apply the operation again to the E, it's going to apply to both of them, right? So you're not going to get, so both of them are going to be transformed to F. So you're not getting, if you realize, these don't actually matter, right? Because you're gonna be transforming them for free when you transform the one that is farthest away from A. So essentially, you want the maximum distance. The maximum distance is the one that is going to determine the optimal, the minimum number of moves that you need, right? And notice that here we have a circle, right? Because it turns around when you go from Z, it wraps around to A, so it's a circle, right? So you have A, B, and so on, and here you have Z. So whenever you have a circle, that means that you should use modulo operator, right? Which is like clock arithmetic. So here we want the distance from our character to A, right? And to calculate the distance, you do the same thing that you do on a linear, if you're in a line, right? If you want to go from X to Y, you do this, right? Y minus X, but here you want to do it mod 26, because that's the size of the alphabet of the circle, and that's going to work. This is going to work because for A, here I'm assuming these are numbers, right, that I can subtract. So you have to apply the ORD function in Python to get the number corresponding to the letter. But yeah, this is the idea. You just do the destination minus the source mod 26, and it's going to work. Notice that if it's an A, if you want to go from A to A, it's going to be 0, so that's going to work, and so on. And so it's pretty much just the maximum of those. So I'm even going to write the function, right? Because I like this. I like to so the source and the target, and I just said I want to do the index of the target minus the index of the source mod 26, right? So that's my distance function. And then I'm going to return the maximum distance from x to a for all x's in S, right? So this should be it. And it works. Yeah, and I like this way of implementing it. I feel it's more principled in the sense that we're defining a distance in clock arithmetic. And yeah, notice that this is not necessary, the transforming this into a set, but surprisingly it makes it run faster, because here it run in 41 milliseconds, and if I remove it, it runs in a lot longer, right? 800. It's a little surprising to me, but I think the reason is there's probably, so there are almost 1,000 test cases, and I'm assuming that on average they are quite long, because the strings can be I think 500,000 characters long. So that really adds up, right? If you have 1,000 test cases, and let's say that on average the number of characters is like 10,000, that already is 10 to the 7 characters that you have to process. And so if you are doing, if doing this operation takes something like 10 to the minus 7 extra than just creating the set, then that would add 1 second, right? So that's the intuition here. I think that that's why it's a little. So I would have thought that creating a set is costly, but it seems like it's not that much. Well, because it's a small set, right? Because it has 26 characters only. So that means that it's going to be efficient. So what did you think, Lucia? Is this what you were thinking? I like the idea of that essentially it is reduced to the farthest distance. My first intuition was I would need the sum of the distances instead. Yeah. Right. The sum of the distances. Yes, this is what I explained here, right? When I showed the strategy. So the strategy would be to start from the farthest letter and start applying the operation to that one, and so that's going to include any other letter in the path from the farthest to A, right? It's going to include all the others for free, and that's why this is the maximum and not the sum, right? So this is how I explain it. How I explain the strategy, and then it boils down to this, right? And so I think that's it for this problem. But yeah, it's interesting. The difference in time and runtime is interesting, because it's a little unexpected for me. But I think the intuition is that there's a lot of characters in the test cases. There are like 10 to the 7 characters. So even if you waste a tiny little bit of time on each, more than you should, or than you could, that's going to add up, right? So 10 to the minus 7 is a tenth of a microsecond, right? So that's very small. So I think that's my explanation. Okay, let's go to Q3. Sounds like an idea that could be reused in other problems. Yes, for sure. Yeah, the idea of... well, you mean this idea of moving... Yeah, you're moving the farthest away from the target, and then anything that is on the way you get for free, right? You move them for free, right? If you can apply one operation to all the occurrences, then all the others you do for free, so it's just the maximum, and there's no sum. So yeah, it's a pattern that could come up. So okay, so let's think about this one. Count bowl subarrays. You're given an array nums with distinct elements. Okay, so let's pay attention to this distinct elements. So a subarray from L to R of nums is called a bowl if the subarray has at least length 3, and the minimum of the two ends is strictly greater than the maximum of all elements in between. Okay, and here's the formal statement, but we don't need to reread that. So return the number of bowl subarrays in nums. Okay, so first thing that you need to do is to make sure you have an intuitive sense of what this bowl thing means, right? So if the two ends are strictly greater than the maximum of the elements in between, that means that they have to be the maximum and the second maximum, right? In the subarray. So that is the only option. So that I guess that you can think visually as a bowl, because those are the in the ends in L and R, you have like the highest like the barriers, and so it's a bowl. You can put your cereal or your on it. Can I draw it? Yes. So yes, you can think of the numbers visually. Like here you have, I don't know, you have 5, right? And then here you have 4, and here you have something like this. Well, here is not clear. Let me be more clear. So, well, they are all distinct, so this is not exactly possible, but it doesn't matter. This is so yeah. So this is your bowl. So here you can put some liquid on it, right? This is your bowl, because the water is not gonna, the liquid is not gonna come out because the ends are higher than everything in the middle, right? So this is our bowl. Cool. So any ideas of how to tackle this? So the shaping between the edges can be whatever as long as it's lower. Yes, exactly. So okay, so the constraints are the size is 10 to the 5 with, as usually it means, this is how you have to translate this. It means that you cannot do something quadratic, right? That would be too slow for 10 to the 5. So you have to do something like linear or n log n. In any case, sometimes it is useful to think about the quadratic solution and then optimize it. That's sometimes one approach to this kind of problem. Because sometimes it's not trivial. Sometimes like the trivial solution is actually cubic, and you have to do something to make it quadratic, and maybe that leads to some optimization. But so do you have any ideas, Lucia? So I think here we have not yet no idea. So okay, so I think one strategy one strategy. So here we have too many moving parts, right? We have so we have a start and then a right hand side of the subarray, right? So and this could be anywhere, this could be anywhere. So let's just fix one of those, right? So we have too many moving parts. What if we knew? What if we knew what R was, right? What if we knew? And then we only think about moving L, right? So let's keep thinking in this visual term, in this way. So here we have some number, right? So like we said, so if this is the right edge of the subarray of the bowl, then we know it has to be either the maximum or the second maximum, right? So let's consider again we have an uncertainty, right? It could be one or the other. So let's think about what happens if it is the maximum. And let's try to grow it from here. So let's say here we have this. So notice that we cannot have anything. If this is going to be the maximum, then if at some point we find something that is greater than it, then of course we have to stop, right? We don't have to search more for any bowl because we know there's not going to be any bowl where this is the maximum, right? But here, so here if we have something like this, well, this could be a possible L, right? Because this is a bowl, right? It looks like a bowl. But then what if we have something like this? Then this is also a bowl. This is another possible position for L, so this is another bowl. Are we doing mono stack? Well, not yet. We're just thinking. By the way, welcome, Bobby. How are you? So here we have another, and maybe here we have this, and then we have another one that is greater, and so here we have another L, another possible L. So we have 1, 2, 3. All of those are possible L pointers for this R, right? So that's interesting. But what if we assume, so we assume that R was going to be the maximum, but what if it's not the maximum? What if it's the second maximum, right? What if R is here, and we say is the second max? Well, now it seems it's a different situation, right? Because if this one is the second max, then we have to look for one. We have to move here, and we have to find the first one that is greater than, because that's the only way. So L is going to have the maximum, right? And so we have to search until we find, let's say here, we find one that is greater than it. So this is the possible L. But now, notice that there cannot be anything, there cannot be any valid L here, right? So we cannot have another L here. No, we cannot have, because if that were the case, then this would be breaking the condition for the bowl. This would be breaking the condition for the bowl, right? Because we cannot have one in the middle that is greater than the edge, the right side, right? So that's interesting, because that means that when we assume that R is the second maximum, there can be only one. There can be only one L, only one L for this R with this assumption, right? And so we just have to, so how do we know if there's an L? Well, this is what you said, right? We want to find the first one that is greater, right? So that's why you're talking about mono stack. But notice that we don't need that. We don't even need that, because we are not going to, we're not asked to find the bowl, right? We're asked to count them, right? So there are two options, right? If when we start here and we start searching, there are two options, right? We never find one that is greater, right? So all of them are below this, and in that case there is no bowl that ends at R, and R is the second maximum, because there's no greater element to the left, right? Or if there is one that is greater, then that means there is exactly one bowl, right? So how do we know that? Well, we can keep track of the maximum to the left, And then we can know if there's one that is greater to the left, right? We compare nums of R with the maximum to the left, and if it is greater, it means that there is exactly one bowl, and if it is not greater, then it means there's no bowl of this kind, right? But be careful, because there's also another condition that the length of the bowl has to be at least 3, right? So that we can cover that by just asking whether the neighbor is less than it, right? That's going to cover, because if we have a neighbor that is less than it, and then we have one somewhere here that is greater than it, then it's going to have at least 3, size 3, right? So this algorithm is going to find all the bowls that have R as the second maximum, right? But what about the other bowls? What about the bowls that have R? We just keep the max to the left. So we go from left to right, and we keep track of the maximum so far, and we compare the R with the maximum to the left and with the previous one, right? And that's gonna tell us if R can be the right side of a bowl, if it's the right side of one bowl. And so we count it if it's true. But what I was saying is that this is going to count only this kind of bowl, right? What about the other kind of bowl, the bowl that has the maximum at R, at the right side? Well, we could do, what if we did this in a function, and then we call it again with the reversed array, reverse input? Then now the ones that had the max to the left are going to be the ones that have the max to the right. So we're going to count the other kind of bowl, right? So that should be our way of solving this, right? So we can say, so count left bowl, right? Which means that these are the bowls dry run it. So why only the second max? Because turns out that if I assume that R is the second max, there's only one possible L that could be matched, that could form a bowl with it. So it's simpler. If R is the max, then there could be many left pointers for it. But if I count this kind of bowl, and then I reverse the thing and count again, and do the same thing again, I'm gonna count the ones that have the second max to the left, right? Because it's reversed. No, we just no, we first said, so the first takeaway here is that when we read this, we realized that L and R have to have the maximum and the second maximum. You cannot have the third maximum. This is the definition of a bowl, right? So we're gonna keep track of the maximum so to the left, and initially it's going to be 0, and we're gonna go from the second element, right? Because the first element cannot be the end of the right side of the bowl, right? And we're gonna ask if the, well, let's call this R because this is our R, and so we want the neighbor, the one to the left of R, to be less than it, and we also want the max to be greater than it, right? If that's the case, then we found a solution, and we update the max, and that's it. And so count left balls of nums, and now if we did this, we're gonna count the right balls. Count left balls. And this is it. No need for monotonic stacks, right? Because we don't need to find the balls. We just need to count them. Turns out this one ended up, I find the monotonic stack solution simpler though. Well, I mean, for what it's worth, that's what I did during the contest. But I think this is the better solution. Once you make when you have this understanding. And I also like this idea of reversing, counting one type of bowl and then reversing. That's pretty neat, in my opinion. So here's the code. I'm gonna add the submissions when I upload this to YouTube, as usual. So let's now. I thought one way was good enough. You mean this? Well, no, because here we're counting left balls, right? Well, I define left balls as the ball that has the maximum in the left end. So the way I describe this, I was assuming that R had the second max, not the max. So there are two kinds of balls, right? The balls can be classified in two, can be partitioned in two, right? You can have this type of ball here, where the right side has the maximum, but you could have another kind of ball where the left side is the maximum, right? And those two are exclusive, right? And so if you count one kind, you count the other kind, and you add, and you have all the balls, right? And the way I designed the algorithm, I was assuming that the maximum was going to be at the left side. So I'm only counting the balls that have the maximum to the left, and then I use this trick of reversing so that the left balls become right balls, the right balls become left balls, in the reverse array, and so I run the same code to count the left balls, but I'm actually counting the right balls because it's reverse, right? So sometimes there are ideas that maybe you don't come up with them. Maybe you find them not intuitive. It's not what you come up with intuitively, but that doesn't mean that the idea isn't good, right? So maybe if you learn it and you start and you get experience with it, then it becomes intuitive, right? Intuition, it's a mix of, so it depends on experience, right? There are things that you get familiar with. So these ideas of doing transformations, these are very useful ideas in competitive programming. So don't shy away from them, even if they sound weird at the beginning, because it can be applied in a lot of problems. So let's move on to the last one. Monostack wasn't intuitive at first. Yeah, I mean, well, monostack is an idea that it's like a tool that you learn and then you apply it, and so I know I need to find the next one that is less than it, or the next one that is greater, right? And you apply that tool and you can find that out. So that's why I did that during the contest, because I thought, okay, the left hand side of the ball is going to be the next one that is greater, so I know how to calculate that with monostack. So I just did that I stopped thinking, but then afterwards I realized, well, I don't need that, right? I just need the maximum. So let's move on to Q4, which I think it's pretty accessible. So pay attention, because even if you usually don't get Q4, I think you can get this one. Hey, Path. Welcome, Path. If you don't follow Path, you should, right? He's the famous LeetCode. So a non-negative integer is called binary palindromic if it's binary representation written without leading zeros, reads the same forward and backwards. Okay, this is the usual way you would define it, right? And return the number of integers k such that k and the binary representation of k is a palindrome. The number 0 is considered binary palindromic and its representation is 0. Alright. Yeah, 0 is kind of an outlier, right? Because all of them start with 1 except 0. Okay, and n can be up to 10 to the 15. So let's see what we can do. So I think here, so one thing that you need to notice with palindromes is that, so let's say we have 5 digits, right? So if you have a 5-digit palindrome, you will have, so it will start with 1, right? Then it will have there's 4 more digits, But notice that you can select, so this is, you can select this part here, and notice that this is going to, this has to be the same, right? Well, actually, this has to be a 1 as well, sorry. And this has to be the same as this. So what I'm trying to say is that this is the only part that is free, in a sense, right? Because once you determine these two values, you can put anything here, but this is not free. This is going to be determined by whatever you put here, right? The stream has an older title. You mean, but isn't it LeetCode 466? Oh, maybe I didn't update it. Yeah, I think I forgot to. Thank you, Urinator. So notice that, yeah, so there are only 2 digits that are free. So if you want to, for example, if you want to count how many there are, so here we have 5 digits, right? And if you have 5 digits, there are 2 that are free, and each of them has 2 options, right? So this is 2 to the 2, right? There are 4 numbers, so they're going to be 0, 0, 0, 1, 1, 0, and 1, 1, right? This is the only thing that matters, right? This is numbering all the, here all the other digits are going to be determined, right? For example, here here you will have a 0, a 1, and a 1, right? This is already all determined. And so and when you have, this is the case of a odd palindrome, right? But if you have an even, and let's say it has 4 digits, you're going to have a 1, and then something here and here, but this is the only one that is free, right? Because this is going to be the same. And so here you have only two options, right? You have 0 and 1. And so if n, well, if any is the number of digits, then I think if you subtract 1 and divide by 2, and that's going to give you how many free binary digits there are in the palindrome, right? So 2 to this is going to give you how many there are, right? So that means that we can start by counting the number of digits, let's call it ND, of binary digits, right? It's going to be bit length. And so, well, first of all, the case where with 1 digit, that's a special case. So let's deal with that separately, because if it's 0 or 1, then for 0 we have to return 1, right? And for 1 we have to return 2. So it's 1 more. right? So now we know that the number it's going to have more than one digit, binary digit. And so my solution, yes, I think it is. And so now if I do I'm gonna count the two numbers that have one digit. I do this separately because 0 is a special case, right? And now now I'm gonna go over from 2 digits and less than the number of digits that our limit has, and I'm going to add 2 to the, and the thing that we described, right? It was q minus 1 divided by 2. It was that, right? And so the number of digits minus 1 divided by 2 rounded down, right? And this works, right? Because here, when I have 5, minus 1 is 4, divided by 2 is 2, so there are 2 free digits. And in the case of 4 minus 1 is 3, divided by 2 is 1, so there's only 1 free digit. So it works for this an even and an odd example. But are they always less than or equal to n? What do you mean? So okay, so now I counted all the digits, all the numbers that have less digits than our number, right? What about the numbers that have the same amount of digits? Well, let's think about the case of 5 digits. Let's say it has 5 digits. So we have 4 numbers, right? So here, notice that so n is our limit, right? So we only care about, well, we first want to look at the free part of n, right? So let's say that it's 0 and 1, right? And here we have something else that we don't know yet. We don't mind. So notice that, well, maybe let's choose this example. So let's say our 5-digit number starts this way. So notice that all the numbers that have the free part that is less than 10 have to be counted, right? Because those are going to be less than our number, regardless of what's here. So those numbers we already want to count, right? So, and how do we count those? Well, we want to extract this number, right? This is the number 2, right? 1, 0. And that's the number of palindromes that are less, right? That have a number that is less in this case, right? So in other words, we have to extract this number. How do we extract this number from our... So there are different ways of doing this, but we can the left, we can break down the digits into two parts. The one that includes the this, right? This is the part that includes the free part, right? And this is the rest. So we want our number, we want to shift it nr times, right, to remove the part that is not free. And then we want to subtract this, right? Because yeah, I think that's correct. So here in the case of 5 digits, right, we have the way I define this, I have NL, so the left part has 3 digits, and the right part has 2 digits, right? And so what I'm saying is that I want to shift NR times, right? So from this number, if I shift, I'm going to remove this part, and then I want to subtract this, right? Which is 1 shifted 3 times, right? Oh, no, but it's not 3 times, it's 2 times. It's 1, yeah, so I think it's NR. But does it work with the even part as well? So here we want, here it's 2 and 2. No, I think I know what it is. It's NL minus 1. Yep. Cool. And so, and now we have only one thing else to do, which is, so we counted the ones that are less. We counted the ones that are less than, that have the free part less than our number, right? But what about, but now we have to figure out the ones that have, the one that has this, the free part equal to our number, right? So we have to check if that palindrome, right? What is it? What is that going to look like? Well, it's going to have this, and then it's going to have this here is going to be the same thing as this, right? Because it's a palindrome. And we want to check if that number is also less than or equal to n, right? So we have to create that number, and we want to check if it is less than or equal to n. So we have to so the way we create this number is we also do this. And then we do this. So this is going to turn off the right hand side of n, right? Which is what we want. And then, and we want to check if this is less than or equal to n, right? Because that's going to mean that we need one more number, right? And so, but now we need to OR it with this number reversed, right? So this is yes, I think so. Reverse is going to just do this, right? We just want to do the usual okay. Cool. So this was the the part that maybe I did not explain, but the idea was that so yeah, this problem boils down to once you know what you're doing, then it boils down to translating these operations into binary, into bitwise operations, right? To do this kind of manipulation. Because so the problem, the idea of extracting this part and reversing it and putting it here, right? You can explain the algorithm in those terms, in those high-level terms, and you would have the idea, right? And then you have to translate it into bitwise operators. But it's good to be able to distinguish between both, right? But yeah, this is logarithmic time, right? And it runs pretty fast, 2 milliseconds. So I don't think you can do better than this. But yeah, so notice that this structure of palindromes, this is something that comes up a lot because so you had to do more case work. Okay. Yeah, so I did some cases, but then I unified them, right? Because I figured out this way of dealing with odd and even, right? By so in the end, there's no special cases. Well, I do have the special case for 1 digit because that's kind of annoying. The fact that they made one. Yeah. Well, I mean, whatever works. But yeah, what I was saying is that this structure of palindromes is something. So notice that it doesn't matter whether it's binary or base 10 or whatever base. This idea is still gonna work, right? And this structure is good because in many problems, one strategy is to generate all the palindromes, and it's the same idea, right? You generate this part, the free part, you generate this part like with a range, right? One by one, and then you fill up the rest, right? You do the reverse thing and so on, and you generate all the palindromes, and there are many problems in LeetCode that one case for no pivot. You mean odd and even? So yeah, the way I generate them, I do not have a special case for odd and even. I just do something similar to this, and it works. But yeah, so here, well, actually, in this problem, the first idea when I first read it, I said, well, can I generate this? Can I generate them all? Because if you generate them, then it will be trivial, right? You would do like a binary search in a list, and it would be done, right? But it turns out that it's too much, because, well, 10 to the 15 is about, remember that if you divide by 3 and then multiply by 10, you can get the equivalent, the approximate power of 2, right? So that's 2 to the 50. So so the numbers can have up to 50 binary digits, and let's say that the palindromes only have half of those free, so this 2 to the 25, and that's 32 million. So it seems doable, but those are only I think you have another factor, because that's only counting the ones that have 50 digits, but then you have all the lesser digits. So I think you have to multiply with another factor, and then it becomes too many. I did try it to see if it worked, but no, you get TLE in the pre-calculation. All right, so yeah, so I think this was a very doable Q4. I think 1,000 people AK this contest. Well, this is without. I don't think they removed all the cheaters yet, but still, it's a lot. 1,000 is a lot. Maybe some people. So I think that even Q3, the explanation was clear. Thank you. Even I might say so. Q3 could be even harder than Q4, I guess. Well, it depends, but I felt that Q4 was more straightforward. Anyways, that's all I have for now. So thanks for watching, and join my Discord. Oh yeah, I'm gonna upload in a moment the YouTube video. So thanks for watching. So bye bye guys. See you later.